So hello everyone. So welcome to join our today's seminar. So this is our first seminar in the May. So I'm Tom. I'm very happy. It's my honor and also very happy to invite Dr. Han Hao to give a speech today. So he is the staff scientist of the Acceleration Consortium at the University of Toronto, and he was also a postdoc fellow with Professor Alan from the chemistry department at the University of Toronto. His research focus includes advanced automation and digitalization of the chemistry, robotics in chemistry, high-assisted molecule design, and high-throughput computation. He also works on delivery design and blueprints for the self-driving lab community. And also Professor Alan is the people who invented self-driving lab this term. Yeah, so that's all. So welcome.
Thank you, Tom, for your kind introduction. And thank you for giving me this opportunity. It is my great pleasure to give this speech. And actually reminds me of something like 14, 15 years ago. I went to Sydney to do something like one-term exchange. Sydney is a very beautiful city. I still miss it. Okay, so today I'm going to talk something about self-driving labs and giving the organic laser project as an example, follow up going to the Acceleration Consortium. So my talk generally has three parts: material, acceleration, and organization. For the material side, let me introduce organic solid-state lasers. On the right side, you can see a traditional four-level system for lasers, but today I'm not going to talk about details of physics. Instead, I'm going to talk about our material itself. In a traditional material discovery, it is actually a very labor and time-intensive process. Usually people begin with humans and sometimes nowadays using computers to do design and then synthesize the compounds, go for some fabrication, and then test the device. This runs to several hundred runs. Finally, we go to the scaling. It actually usually for traditional material, it takes something like $10 to $25 million and 10 to 25 years to bring to the market. Let's take organic LEDs OLED as an example. It was discovered back in 1987. Dunn et al. Discovered the first OLED molecule, and then the first spin-off from Princeton was something like 1994, but it was until 2007. Something like the Samsung developed the first OLED phone. And nowadays, if you actually look at their phone, pretty much they have OLED screens. It has kept something like billions of dollars of market shares. And when talking about OLED, there's one name that should be mentioned, Chihaya Adachi. He actually is the third inventor of third and fourth generation OLED. Actually, with his TADF molecule, we were able to achieve 100% quantum yield with the electropumping system. So one challenge that Chihaya found is that even with his most advanced TADF and high-performance molecule, the brightness is not enough, and the color purity is usually has 20, 40, at least 20, usually 40, 50 nanometer half weight. That means they are not ideal for display. As a result, he devoted to discover the lasers using OLEDs. So, for example, for example, this molecule, we call it BSBCZ, has very low AFE threshold that with only something like 1.8 microjoule per centimeter of irradiation, it can lace. Furthermore, he worked on something like solution process for lasers, enhanced stability, and so on. The challenge is that this molecules is very annoying to synthesize, and also optimizing it is even more challenging. Even with Chihaya's lab, there's only 10 materials roughly in 3 years. Of course, we can still wait for it, and maybe in 2030, 2050, 40, we have organic lasers on our phones. But is there a way to accelerate this process? Answer is yes. And this is the second part, self-driving lab and AC/DC workflow. So when talking about organic lasers and also similarly organic photovoltaics, there has been lots of effort using computational resources to accelerate this process. One common thing applied in OLED screening, as well as many drug molecule and other small molecule screening, is actually doing the virtual screening. We first generate a huge library, and then using machine learning to predict some properties. Based on the machine learning predicted properties, we select a smaller fraction to do quantum chemistry, and then we go to roughly 1,000 or so candidates, go to real synthesis, and get the desired molecule in a device. This process has been run for many projects, including Harvard Clean Energy project for solar cells, and also recently a few OLEDs with Marty Berg. The challenge is that from here, the library generation all the way to the expert selection, they can be done automatically. But in a real lab, getting from here to here is very complicated. This is where self-driving lab comes in. So in current material development, as we had said before, we usually have the material conceptualization, and using human or computational tools, we can do lots of molecular design, and then we have to human to do the synthesis, device fabrication, testing, and then go back to the loop. It is a relatively labor-intensive process. Instead, in a self-driving lab, not only we have the computers doing an AI doing the inverse design using simulations and genetic process, we also have the AI to do optimization and using robotics to do the make test analysis. By doing this in a closed loop automated fashion, we can accelerate this process by tens, hundreds of times. One thing I want to correct Tom is that Alan did not invent the keyword self-driving lab. It is self-driving lab. It was actually introduced really a while ago, back to the 1978, where people were using PDP-11, a 16-bit chip, to do the closed-loop discovery. The challenge is that with back to the 70s, 80s, or even at the beginning of 2000s, the computational power as well as the automation technique does not allow us to do actual dynamic self-driving labs. So this is actually a recent review by MetaLab and Acceleration Consortium. So traditionally, people have been doing something like human idealization to conceptualize and manage synthesis, which we call it level 0 SDL, which is very fundamental. And with the more advanced automation like peptide synthesizer, etc., that's level 1 doing single task, and add weight to something like level 2, which can do workflow. On the other hand, we have something like single iteration design of experiment, and then using machine learning to guide the design. By merging these two, we can go to level 3 and level 4 SDLs. And ultimately at level 5 is the autonomous. Here are a selection of examples of running SDLs. For example, we have Lee Cronin's computer. We have Andy Cooper's mobile robot. We have something like based for molecular optimization. We have the large language model for the molecular design. All of these are very fantastic. The challenge is that if you look at the BOM list of each of these labs, it will be hundreds or even millions of dollars. And even for the computational resources, it is very expensive. It is therefore not very easy to have something like one self-driving lab to do everything. So to address this problem, what we propose to actually realize the level 5 autonomous self-driving lab is carry out worldwide delocalized SDL. So this one we bring to the Mathis team, which is we have a joint task force of 5 leading figures, actually 6, including Chihaya Adachi, who I introduced earlier. Alan, my postdoc supervisor at Toronto, Marty Berg at Champaign, Lee at Glasgow, Bartos from Warsaw, as well as Jason at UBC, where I actually did my PhD in UBC. He was one of my committee members. So these are the leading figures in the world on self-driving lab, bringing the most advanced automation and AI for the development of new materials. To carry out this campaign, we of course begin with the chemical space. as a starting point, we choose the state-of-art BSPC molecule, and then we build a functionally encoded search space. This is virtual space. How do we go from this Cambridge core structure, the virtual space, all the way to this kind of bright molecules in Jason's hand? A reminder: this molecule is so bright, it is irradiated and fluorescent under the light of a screen. It is not using any UV torch. So, just like how we do self-driving cars, we need to build wheels for the self-driving labs. So at the beginning, we were thinking, okay, we want to assemble the molecules. One of the most reliable reaction to make conjugated materials is Suzuki coupling. So, okay, but many of the reactions is not given well. So we say, can we use AI to process literature to find the optimal conditions? The answer is no, because literature is highly biased. You can simply use something like literature parsing to generalize the general conditions for Suzuki. It actually failed. This was done by Bartos and Bartos group. And after that one, Bartos people works with Martis people actually doing the closed loop optimization of general conditions of Suzukis. You may think 21 to 46% improvement is minor, but remember, Martis group spent something like 15 years on optimizing Suzuki conditions, and within only something like 6 weeks, they were able to beat their previous record, and with only 3 rounds of experiments. This is a fantastic improvement. Okay, and then to actually look into the to get the material for OLEDs, we also need something like a real scale up and also get the pure materials. This is where Jason contributes a lot. So what we do is that we have our online monitoring mechanism, and then based on the reaction progress, we do active decision making. Using this way, we are able to suppress the byproduct. Here you see the black dots. And then we can improve the yield from 7 to 50%. Also, we were able to actually get something like we were able to have continuous crystallization to purify this molecule, this kind of conjugated molecule, which are insoluble in most solvent and very hard to purify. So, and now we have built all these things. What we do in Toronto is actually an even more complicated thing. First of all, we need to build the automation workflow to actually synthesize and characterize molecule. Here, we combine the established commercial platform, the ChemSpeed, together with the home-built optic table. By having by synchronizing all the platform HPLC to MS to optics using a standalone Python orchestrator, we are able to get high-quality spectroscopy data within 30 minutes. By using this one, Tony, the first postdoc carrying out this project in Toronto, discovered something like 10 good molecules within 40 candidates that suppress BSPCZ and perform similarly in film, that is within something like 1 or 2 rounds of experiments. So now we have our power tool to do end-to-end automation to get organic lasers. But let me remind everyone that our key approach is actually having worldwide localized SDLs. That is how we can assemble all the wheels that I mentioned before into a self-driving lab. So this week they're talking about KDL, which was invented by Lee Cronin. So it is a general chemistry script, just like the script you run on your computer, but instead it runs the computer by Lee and also other platforms. By encoding all the chemistry synthetic knowledge as well as metadata into the KDL, what we can do is that we have one reaction running at Vancouver with 59% yield, upload to the cloud, and Glasgow on the other side of the Earth, download the KDL, get exactly 59% yield. And then Glasgow did some precision, 72, upload, download at Vancouver, again 71. Anyone have been doing organic synthesis may realize this is something like even hard to achieve within one single lab. Now we are doing it at different hemispheres. From Vancouver to Glasgow, and maybe from Toronto to Sydney. So now we have all the pieces. We now stitch it together with a cloud-based center that can orchestrate, that can manage all the process from building block synthesis at Vancouver and Glasgow, to the 4 molecule synthesis at Toronto as well as Urbana-Champaign. So at the beginning, okay, we need to demonstrate our workflow works nicely. Here we down select 500 candidates, and within only 3 months, we make all the 500 laser candidates and get them fully characterized. Let me remind you, the very beginning, with characterization approach was 10 molecules in 3 years. With Tony's single-site SDL automation high-throughput experiments, it's 40 molecules in 1 year. Now with SDL, we can have 500 in 3 months. The challenge is that most of the molecules we screen in the initial state, they are poor lasers. If you look at here, and only a handful of molecules that are better than BSPCZ. We say, okay, now it's the time to employ AI for the design. But the problem is, even with the most advanced, before we actually develop the AI algorithms, we need to make sure we can represent our molecules, because our computers are based on silicon. It doesn't recognize CNHO. So for doing this one, we first, okay, let's see whether we can represent this. And we found that most molecular representations like fingerprint, smile string, etc., they do as good or as bad as one-hot encoding, which basically called molecule 1, 2, 3. So what we do is that we carried out a high-throughput computational workflow, and then by doing this one, we can get some correlations. The key thing is that for the 200,000 model we calculated, we need to we get all DFT descriptors, and then we can train a graph neural network that can predict the property on the fly, and then this one will allow us to search on the graph neural network surface instead of searching for all the 200,000 molecules with something like I think it's something like 80, 90 descriptor molecule. That is something like millions of descriptors. And now by removing the last layer of GNN predictor to the base optimization, we can actually run a base opt. And here is how our GNN projected to a 2-dimensional UMAP looks like. You can see most of the great molecules, they actually lie at the tail of this jumping unicorn. So for the base opt, okay, it is something like people may have been reading, chemists have been using base opt quite a bit. By the way, I was surprised that several scientists from Google DeepMind, they didn't know chemists have been using base opt. Anyway, for a real chemistry campaign, especially with a delocalized experimentation, we cannot do the traditional base opt that we have one batch of results, update, retrain our model, and give new recommendations. We will be blocked by something like shaping or data availability or human availability. What we do is that we have something like a logical informed AI that understands what is being done, what is to be done, what is failed, etc. And then by doing that one, every time with a new molecule new data point come in, we can update our model and keep our recommendation pool the freshest. So now here is how our optimization goes. You can see at the beginning of the screening, we have some rapid growth, and then it plateaus because it is already at the edge of something like the traditional human-based design. And in the high throughput screening, we actually don't find any good molecules. But after we start our AI-assisted discovery, you can see this tail up. This basic tells that we can find molecules much faster than the not only the human-based design, but also the high throughput experimentations. So finally, we were able to get this kind of molecule that we can purify on gram scale, and then we identify that it has actually the lowest AIE threshold ever, roughly 1.6 microjoule per centimeter. So this is actually a fantastic approach, but the thing we learned is that by combining AI and automation, we can develop SDLs, and especially with something like SDLs across different disciplines, we can do things much better. And all of this leads to the third section, which is Acceleration Consortium, how we build the ecosystem of SDLs. So Acceleration Consortium was something like when Alan came to Toronto, he started a consortium that is from very small, try to bring people that are interested in AI and automation. And then after we proved that actually with the Magnet campaign and several other campaigns, we can actually accelerate material discovery to a speed that is faster than ever. We were able, we got the $200 million grant from the Canadian government, the biggest ever, to develop the new hub for the accelerated discovery. So based at the University of Toronto, the AC is a global community of academia, industry, and government that is accelerating the discovery of new materials and molecules for a sustainable future. So since we learned that we need something like multidisciplinary co-effort to move forward the self-driving lab community, we actually developed not only one lab here, but an ecosystem of 7 labs, or actually 8. So SDL1 inorganic, SDL2 organic, SDL3 medicinal, 4 polymer, 5 formulation, 6 biocompatibility, 7 scale-up. We also have our supporting lab, like the AI automation lab, social science lab, and training lab. As the core of the AC is different from the traditional, okay, we have something like university center that has a few professors have their name on the list and they still run their own group. What we have is that core faculties, including the staff scientists, 30-35, and we have our software engineers developing software. We have our staff scholars doing the humanity research, and we even have our product managers and business development team to actually promote us as a central hub. So and then the next, I'd like to introduce each SDL one by one. So first is SDL0, which we call AI and Automation SDL. This SDL is led by scientists Cross, Mirad, Sergio, and Sterling. Their key focus is actually developed the most advanced robotic automation, including using computer-based human robot teams, human robot trimming, and to do the interface with humans in the new SDL. As they are also doing AI and lab orchestration things. Some recent achievements, including, for example, using AI hub for some using AIM interfacing for the molecular design. Also using something like using digital twins to do the experiment planning and pre-training. For orchestration, we can actually manage the lab more cleverly, and I will talk a little bit more when I talk about SDL2, my SDL. So SDL1 is the inorganic SDL. It is led by Kangming, Ali, and Yang, and I think they have recently had just onboarded, a new scientist. Unfortunately, I've got his photo here. We also have the faculty, Dave, Jay, Mohammed, Yu. So in this SDL, they basically focus on electrocatalysis and electrocatalysis, and also something like high entropy alloy and anti-corrosion materials. So what they're currently working on is more something like electrosynthesis platforms, and especially on the OEI HEI reactions as well. So here is actually one of their building things, building something like automated electroplating station using cheap open trans robot, and also with something like multi-electrode high throughput screening platforms. So an SDL2 is actually SDL I'm working in. So we are my team member, including me, myself, and Yang, my old friend, back to my PhD study, and also our new scientists, Eric and Xiaoman. So we have our faculty, Sophie, as well as Len, to support us. What we focus on in SDL2 is generally 2 aspects. So one is chemistry or reactions that is developing new automation technologies, and also we work on materials or applications, including new drugs and restorative materials and something like electrophotonic materials. So what we focus on, so here is here because this is my SDL, I have to introduce a bit more. So we focus on 2 main streams: automation of robust chemistry and automation of challenge chemistry. For robust chemistry, there has been lots of achievements recently going on. For example, actually not recently, back to 20 years ago, it has been using peptide synthesizers and so on for iterating known chemistry one reaction over and over. But it basically stays the same kind of bond and cannot make more complicated structure. What we are working on in the short term is actually program this kind of known chemistries in a more modular fashion to get modular structures. Another thing that we work on is actually for channel chemistry. Mostly have been done is single step high throughput screening. What we're doing working on is actually using AI for exploration and to find the general conditions that we can not only get known structures but also merge with something like modular pathway developed in other branch, and we can get whatever molecule on demand. So some recent achievements, for example, we have the nature extension of our organic laser project. In this extension, we were able to push forward the organic lasers from the purple blue region all the way to yellow and even red near IR region. So this BT12 molecule that we were able to explore more it actually shows the lasing property and has something like has the ASE threshold has the threshold similar to what we discovered early on with the blue laser. This one fantastic thing about this one is that the whole project was carried out not with 5 teams that working very hard day to day for 1.5 year. Instead, we have only one PhD student doing our workflow, and everything roll out so easily. So this is the transferability of our SDL. And some other workflow that we have been doing is actually demonstrating the something like the cross-site collaboration. This is actual collaboration between us and the UBC scale-up team. So so what we do is that this is again lies into our concatenating known reactions. Here we know that okay, we have for the organic reactions, 80% of time actually happens in the purification and isolation process. In this work, we work with industrial partner, namely BMS, to develop the automated liquid extraction SDL. Here we have our automation platform to do the adequate separation, weighting, etc., and have our central AI engine to plan for the next phase of experimentations. So by doing so recently, many big pharmas has a big cut, but our project is BMS survived very nicely. It is because with SDL we demonstrate that it is actually much more fluent than the traditional way of developing pharmaceutical chemistry. And on the Chinese chemistry side, we have been working on, for example, electrosynthesis. But before we do the electrosynthesis, we need to build platforms that can actually do EChem. That was the challenge of doing doing EChem in a self-running lab is that the potential stat and also the power supply, etc., they are from proprietary hardware and hard to control. Instead, we actually designed our own potential stat and redeveloped our Medusa platform that was developed in the Matrix project. Together, we have this platform know from the basic average register all the way to the chemistry. As such, we can actually build something. For example, we can actually build decision making because we know each status of each module of the synthetic and analysis platform, and then we can make the active decision making to tell us, okay, this electrochemistry works nicely, or this needs to change the electrode. So and one key thing that we can actually support this kind of managing complicated workflow is actually our lab orchestration. This is what we call ChemOS 2.0. So if you look for ChemOS, always look for the ChemOS 2.0 because the first generation of ChemOS was, I have to admit, it was more like a toy. But with the ChemOS 2.0, we can have a real orchestrator that manages the resources for not only for the automated hardware like database and experiment planners. Moreover, our orchestrator can talk with the public database as well as external resources. As such, we can see our ChemOS 2.0 to any self-driving labs as long as API is provided. As of a demonstration, we were able to connect the ChemOS 2.0 into our organic laser workflow. One thing I didn't mention earlier on was that for the organic laser workflow, we still need something like we still need human to transfer, for example, the computational data to the something like AI engine, and even we have automated data processing for something like the for triggering the chem speed. It still needs something like feeding this a CSV table, etc. With ChemOS 2, these ones are all automatic, and we do 2 rounds of optimization seamlessly. So okay, and there are also several other side projects that SDL2 and the SDL have been working quite a lot. For example, one thing that we realized when we're doing the electrochemistry project is that our electrode get degraded very rapidly. As such, even though we have our advanced decision making and automation platform, we have to go to the lab every 2 or 3 times a day to change the electrode, which actually becoming our bottleneck. We were interested. Okay, is there any way to we do the electrode refreshment automatically? And here is the answer: yes. You can see we have robotic arm doing the polishing, the rinsing, electrochemistry measurement, and alongside this demo series, we also have the computer vision looking at the surface properties. By doing this one, we were able to realize a fun knowledge. So, how many of you have done electrochemistry? I guess everyone has this experience. We're told, okay, you need to polish the electrode in the figure 8, which is one of the things I hate most during my undergrad. But by doing this kind of using robotics to do the polishing, we found that no matter you do a linear, circular, egg, these are all using a hand. Statistically, there is no difference after 1 minute. So basically, now professors, if your students are still complaining about polishing figure 8, tell them you can simply do linear polishing. And aside from experimentations, SDL2 is also working very closely using the cutting edge LLM to do computational work. This is some recent work we do together with the MATLAB, using something like multi-agent to carry out high throughput computation. Basically, you tell what we need to do with what we need to calculate, for example, the pKa, or for example the structure of a lensline complex, etc. And then it will the agent will design the computational inputs, submit a job, process the data, and tell you right away. It can even correct something like non-convergence issue, or something like dimensional frequencies, all automatically. So and now this is end of what we do at the SDL. Let's back to introducing other SDLs. So for the SDL3, it is actually in collaboration very closely with local hospitals and SGC Structured Genome Consortium. So we have staff scientists, Sasha, Joe, Carla, and Stuart, as well as Sherry and Rob as the consulting faculty. What we do in SDL3 is actually building a self-driving lab for heat-to-lead optimization, and they focus on direct-to-biology testing and AI to affinity selection mass spectroscopies. So recently they have already so after long procurement process, I have to admit one of our biggest enemy in Canada is at the long procurement process. But we were able to, but in SDL3 they were able to build a mini workflow combining the liquid handlers, bioacids as well as preparator, etc. using a robotic arm to connect the whole workflow. And right nearby, there are high-end MS, and they are actively doing the heat-to-lead screenings. So we also have our SDL4 doing polymers, which is led by Nippon, Owen, and Harry. So together with the faculty, Helen, as well as Dwight. So what we do at the SDL4 polymers is actually building automated lab capable of synthesizing, processing, and characterizing polymers. So, for example, what we are doing here is combining a handful of commercial and made in-house hardware to actually do the spectral testing as well as open source photo reaction polymerization. And recently, we were able even to measure having this complete having this end-to-end automated workflow using something liquid handler, robotic arm, as well as mechanical annotator to do the optimization of and screening of mechanical properties. Okay, and now let's talk about SDL5, which we do as in formulations. So for the formulation SDL, it is led by Friend and Aaron, 13, etc., as well as faculty, Christine and Frank. What we do at the formulations, instead of actually looking at the molecules, we look at how the molecules are assembled in a real physical system. What we focus on a lot is semi-solid gels, creams, as well as real world applications. For example, one of the recent projects involving making the best shampoos. So in the SDL5, in the SDL5, they're highlighting the SDLs to accelerate the development of high-performance formulations, especially on the automated formulation preparing and capacity to enhance throughput and efficiency. So you can see what they do for the contact angle measurement. Again, we are heavily using the open trunks, and this is workflow that they were able to build with only something like 2 or 3 weeks, and all this was only enabled by the high-level sharing of knowledge within the Acceleration Consortium. So in SDL6 human organ mimicry, we again have collaborations closely with local hospitals and led by Ilya and Rainy, together with several real doctors. What we in the human organ mimicry things, what we try to do is developing self-driving labs for the human tissue models to improve efficiency, reproducibility, and biological relevance for in vitro organ or organ chip research. So what we do here in the SDL6 is actually doing tissue culture workflows, including cell engineered tissue organoids and organ seeding, passaging, and medical exchange. So by integrating model automation, organ chip platforms, and real-time data analytics let support efficient discovery and validation across range of disease models and toxicity screens. This is what they do from end-to-end automated analysis of a mimicry organ on a chip. Okay, and then finally we have our branch in the UBC side, which is SDL7, doing the scale-ups. So at SDL7 we kind of have 2 staff scientists, Katja and Daniel, and 2 faculty, Jason and Curtis. In the SDL7, they're doing something quite different from what we do in Toronto, which is scaling up. So, so one of the key mission of the Acceleration Consortium is we not only do something like academic research, we also try to connect the academic with the industry, and this is where SDL7 plays an important role. So, in UBC, like Jason and Curtis together with Katja and Daniel, they try to develop something. Like a laboratory operating system, for example, Ivory OS, to homogenize the protocols and to do something like technical transfer as well as condition optimizations. And then after that one, they are doing something like so one thing of the larger scale, for example, from usually in SDL2 doing 10 milligram, 20 milligram, they're doing to 10, 20 gram, even larger scale. And one key focus is actually looking into the real-time monitoring and the kinetics to actually tune the things that are usually not realized in small-scale batch reactors. For example, the heat transfer, mass transfers. So, and then further on, like I introduced early on, we work SDL2 and SDL7 work very closely to do the workup and purifications inter-step and at the end of the experiments to have something like robotic purification, automated liquid extraction, thin film fabrication, etc. So now I have introduced all the SDLs that are doing academic research. We also have supporting SDLs. First, we have our indigenous science and ethics substantial labs. One of the questions that I always been asking is by external people is that how do we ensure something like a self-driving lab is safe and actually is something like sometimes even hear people making joke. How to ensure you're not making the T800? So this is what we value a lot, and in our ethics lab, we actually working very closely with local communities. Recently we were traveling to a nearby so-called chemical valley, which were hurt by chemistry a lot, and actually it's only with the ethics lab we can connect those people who believe chemistry is something bad and hate us, and thanks for with ethics lab delivering our values that is more sustainable, more greener, and collaborate with the community, we can actually persuade the chemical valley residents that we are actually helping them instead of instead of launching another plan that destroys their whole lives. So also we have our economy lab that is try to make sure that our self-driving labs ecosystem is more sustainable. So here with Young, we actually work on a combination of topics across economy of science, economy of entrepreneurship, especially the ones relating to the AI, to realize how and whether automation improves reproducibility, topics around how AI deals with affect science, not only in the scientific product, but also it changes the direction of research, how the community moves. So so by doing so, we can actually ensure a more sustainable future of the Acceleration Consortium, because even though we have $200 million from Canadian government, the grant is only for 7 years. We need to ensure the big academic community as well as the industry will keep funding us to roll in more and more. One thing I want to bring to you is actually to support the Acceleration Consortium. We not only have the 200 million from the Canadian government, we also have the university investing very a lot, which is a brand new building. So I've been living in Canada for something like 10 years, and every time I have been complaining something like fixing the road or something like even fixing a single water pipe, a pipeline or tap takes forever. But I've been seeing the most rapid growth of a new building. Here, this photo was taken something like one month ago, and today before I left the lab, I actually looked up, and we already have the third floor built. So, and then I believe by the end of something like by the end of 2026, we will be able to move in the new building, and we welcome you come to Toronto to have tours in our new SDLs. And then I would like to acknowledge the Astrogoodic Lab of Alain and also Felix, my close collaborator. Also to acknowledge the funding source, the AC, UT DARPA, and also tri-agency for the acceleration. So last point. So we are hosting the Acceleration Conference. We are hosting the Acceleration every year. So I met Tong in the second Acceleration Conference, and Tong also came to the third Acceleration in Vancouver. This year, the AC conference is back to Toronto, and I look forward to see you all in Toronto this August 11 to 14th. Please feel free to scan this QR code to know more information. Thank you.
Cool. Thank you, Han, for your very informative seminar. Yeah, it's truly told a lot. Yeah. Yeah. So, are there any questions from UNSW our side?